All right, welcome back. I just went through this first example, so if you did not watch that first, please make sure you go back and do that. I'm going to start with this second example here, and this says a man 6 feet tall walks at a rate of 5 feet per second towards a light pole 16 feet tall. And the first question is, at what rate is the tip of the shadow moving when he is 10 feet from the base of the light? Excuse me. Okay, so we're going to draw a picture here. We're dealing with a light pole and a light and a person. So I'm going to draw a triangle here. Looks like that. And a man is 6 feet tall and he's walking towards a light pole. So this right here is the light pole. And he's somewhere here. I don't know where, but he's 6 feet tall. So I know that's 6 feet. And the person's height is not going to change. So that's going to be a consistent 6. The other value that I know that's not going to change is that the light pole is 16 feet. So my light pole is 16 feet tall. The man is 6 feet tall. It says, at what rate is the tip of his shadow moving when he is 10 feet from the base of the light? And so this is kind of tricky because you're trying to figure out what's going on here. If you're standing here and the light is behind you, that means this length right here is the shadow. This is the tip of the shadow. And it tells you that a man is walking at a rate of 5 feet per second towards the light pole. So your X value is actually going this direction because he's walking towards the light pole. So we got to take that into account. And so the thing that we are given here, which I will note, is this right here. He walks at a rate of 5 feet per second towards the light pole. And so I'm going to say this is negative 5 feet per second. And that is my dx dt because this is my x value when I'm looking at this horizontally. It's negative because his length is going to be decreasing as he gets closer. So that's why I made that negative. In part A, we are finding the rate at which the tip of his shadow is moving when he is 10 feet from the light pole. And so we are looking for how fast this length is decreasing as he's going this way. Because as he walks this way, this length is going to come towards here until you're all right here. So this is actually, we're going to have to call these some different variables because we've got a bunch of things going on here. So I just called this A just because I could. And then the shadow I referred to as W here just because I needed some different variables because this length here is changing differently than this length here. They're two different lengths. So I have to distinguish that. And then I'm calling this length from here to here X just based on what they're giving me. And so this is kind of the picture that you have to set up. This picture is kind of tricky to get set up, I think. And so we're looking for, again, at what rate is the tip of his shadow moving when he is 10 feet from the base of the light? And so we're looking for dA dt when your X value is 10. Because again, the length from here to the light pole is the length of X. That's what I called that. Okay, so in part A, we have to figure out how to represent A because we're looking for dA dt. And so A is just simply X plus W. So that seems, easy enough. A is X plus W. But remember when we did the problem like this yesterday? We can't necessarily use all three variables because we don't know something about all three variables. We know we're looking for dA dt, so we have to have A, and we know something about dx dt, and that's negative 5. We don't know anything about W. So again, in this case, we need to eliminate W so that our equation is only in A and X. And so this is back to what we did yesterday, involving proportional triangles again. So I know that this length is 16, this length is 6. This whole length is A, and this little guy here for this triangle, I call W. And so I'm going to use this then to help me. I'm going to take 16 over 6 and set it equal to A over W. So 6A equals 16W. And if I'm trying to eliminate W, I need to solve for W so that I can replace it up here. So if I divide by 16, W is 6 over 16, which is, in this case, 3A over 8. So this right here I'm going to use now up here. So I'm going to come back up here. I'm going to rewrite my equation. A equals X plus, this is 3/8 A. And now I have an equation that's only in terms of A and X, which is what I want because that's all the information I have so far. So from here now I can find the derivative implicitly. So the derivative of A is dA dt. Derivative of X is 1 dx dt. And then we've got derivative of 3/8 A again, which is 3/8 dA dt. Like that. Okay, so now that I have this, I can start replacing some things here. Sorry, this is plus. Oh, I have two equal signs. That's plus. Okay, I don't know dA dt. That's what I'm trying to find, but I do know dx dt. So I can replace that with the -5. I'm getting that from right here. That's dx dt plus 3/8 dA dt. So I need to combine my fractions here and move some things over. I'm going to just kick this to the side by subtraction. And so this is like 8 over 8 dA dt if I want to think about it that way. So when I move this over, I get 5/8 dA dt equals -5. And then in order to solve for this, I need to multiply by the reciprocal. So I'm multiplying by 8 over 5. I'll get rid of that. So I get dA dt, my 5's will cancel to be -8. And because this is a length and my units were feet, this is feet per second. So the rate at which the tip of the shadow is moving when he is 10 feet from the base of the light is -8 feet per second on that one. Let's see here. Part B. I'm running out of room here. Says, at what rate is the length of his shadow moving when he is 10 feet from the base of the light? So now we're looking at this shadow, which is dW dt. So it's a little bit different. So we're looking for dW dt. All right. So we're still going to use the same equation as we did before. But now we're needing to be in terms of W if we can. So again, our equation was just A equals X plus W. And I don't have to worry about having different variables anymore in this case because I have something about dA dt, which I just found here. And I have dx dt. So that's going to make things a little bit easier. And we're looking for dW dt, so that's fine. So I'm going to take the derivative, dA dt equals dx dt plus dW dt. So that's that. And I have information for all this except for one of them. dA dt is -8, so I can replace that with -8. dx dt is -5 plus dW dt. And in order to solve for dw dt, I just need to add 5 to both sides. So that gives me dw dt equals -3. This is again feet per second. So that one again was kind of tricky just because the picture was kind of weird. But overall, the deriving part wasn't too bad. So that is that example. If you come back to the next link, I will go through this third example for you.